Not working. Wait a second. So today we'll cover policy iteration, value iteration with some examples as well as the Monte Carlo methods. And we'll study some numerical examples. First of all, before jumping to this, I want to ask like whether this example of MDP, which we have done through value iteration before only with like before explaining, was it clear? Or there are any doubts within that?
For me, it is clear.
And rest of you? Okay, let's proceed. First, I'll write value iteration. Select V naught belongs to V. I'll go through the examples, more examples of value iteration as well.
Yes.
The difference between value iteration and policy iteration, like we'll solve an example, like both value iteration as well as policy iteration, so that we can get the difference. Write it first and then we'll discuss about it. Can someone explain me what I have written on the value iteration? And then we'll go to the discussion. Yes.
Go on operating an L operator on this equation, returns, expected returns.
Okay, line by line.
Yeah,
Let's go.
line, actually.
Select any V naught and then
Yeah.
can someone explain me now? Can you explain me the second line? What is this Vn plus 1 max expected reward? What is this line basically?
Select that action which maximizes rewards, right? rewards.
Okay.
I mean, immediate rewards plus, I mean, a reward of expected reward of next time state.
What is this? Can I say that is a terminate cost? Like this is the immediate reward plus
Next,
the
next, next state, next state value function.
So basically, what is the expected reward if I'm in the state S and taking an action A plus discount factor? What is the
Yeah.
probability now I am in the state S and A that I'll go to S dash and then the terminated cost, that is V pi of 3 dash.
Yeah.
And then this is the
So use either J or S prime for as a loop index.
you're right.
Yeah.
Let's use S prime here.
And then V superscript n, the previous iteration value.
Okay. Yes.
Yeah.
Now Vn plus 1 is equal to LVn. This we have already studied. Now what is this?
This convergence. Yeah.
Can I say that it is a stopping criteria?
Yeah. Convergence criteria. Yeah.
So basically I'll stop we are taking a stopping criteria rather than taking that it should be like the convergence criteria, as you told, that the difference between should be it is epsilon optimal or the difference is Vn plus 1 minus Vn. If we have reached this state, then we'll stop. Otherwise, we'll continue. That is what we are saying. And then this is the what is this basically?
Setting up policy. Setting up optimal policy.
So what is the policy and what is argmax? Argmax will tell us the what at what index, at what
action?
which action. Yes, you are correct.
Yeah.
Which action I'm getting that expected reward as the maximum one. So that is what we'll choose as the optimal policy. Okay. So before jumping to the theorem and proof, let's go with an example and then we'll come back again.
Yes.
So let us take a grid like this. As in the last class, everyone was saying that numerical examples will help, though there are less students today in the class.
Still there are 6. Yesterday there were 2.
Okay. Maybe yesterday was Friday, that's why working.
Yeah.
So basically, these are the states. S00, S01, 02. These are the states basically. And whenever I'll reach this state, S22, let us say the reward is basically plus 1. Otherwise, the reward is 0. Let us take for an example. Now, starting with iteration 1. So, S22, the reward is 1. That is simple. If I say S21, 2, now to reach S22, from S21, what is the reward here? Basically 0 if I'm in S21. The reward for the other states are 0. And the reward for S22 is basically 1. So 0 plus, and let us take as gamma. In this, let us take the gamma is equal to 1. I think I don't have to again tell you what is gamma.
Yeah.
Might be aware that gamma is the discount factor. So 1 into S22. Basically, I'm reaching S21 to S22. Value function of S22, I mean. So 0 plus 1. And S22 value function is basically 1. So any doubts up till now? What I'm saying is the value function of like S22, it is given, the basically reward is 1. So I can say that it is basically 1 here, because when we'll solve it, and S21 to S22, basically the reward is 0 in S21. But when we'll go, like the gamma is 1 and S22, basically value function, we have already told that it is 1. So 0 plus 1 into 1, that is 1 here.
So there are no transition probabilities shown.
No, it is deterministic. Let us take it.
Deterministic. Okay.
A very simple example I'm taking.
But transitions from what to what? All neighboring. I mean, four neighbor four or neighbor eight. What?
So now
Four neighbors or eight neighbors and that like that. What are the transitions? Possible transitions?
so if I'm going from S to 1, so what is the possible transition where I can go?
No, from S2 it is fine, but let's say from S1 or
S1
maybe
1,
others. Yeah.
I have to
So
reach 2
so
2
it's
basically.
four connect. It's four connected. I mean, thing or eight connected thing.
It is
What
4
it is?
connected thing,
Four
but now
connected. Okay.
to reach S22 basically.
S2 one is okay. S2 one is okay.
So S21, okay. Now the next one is, I can say S12, suppose. S12 is similar to S21,
Same.
similar.
Yes. Yes. Yes.
So can I say same thing?
Yes.
If I talk about S11, I have to reach S22 basically. Now either I'll reach to S12, either I'll reach to S21.
Yeah.
Like either I'll go from S12 to S22, or either I'll go from S21 to S22.
Yes.
Reward is 0, discount factor is 1, and we calculated both of the probabilities of S12 as well as S21. Both are 1, so it will make no difference either which of the path we'll follow. We'll get the value function as 1 only. So suppose it's iteration 3 we are doing, and here if I have a
Okay.
wait a
So
second.
what are the actions over here? Go
Hmm.
left, go right, like that.
The actions here are either I'll go right, either I'll go bottom basically.
Okay.
Though we
So
can, though it is just I'm telling you a very basic example. I'll go to more complex one after this one, just to give you an overview. Like if I have to reach S22, I am going either right, either down, just to reach S22. There, when I am updating my policy, like the value functions earlier was 0000. Now what are they? After this iteration, after this one, basically my this is basically 1, I can say, the value functions, and this is also 1. Am I correct?
yes.
Now after S11 is this. What about S02?
Now, do we need to take max? I mean, there are two actions which can take place. Go
Max,
down or
yes,
go
yes.
right. Yeah. Yeah.
But that is what we are saying, that max
Mhm.
will basically same only. Either we can
So,
choose S2.
but we have to write and then select, right? Next time
Ah,
maybe it might not happen.
yes, true.
Yeah.
So
Here
you can,
it's simple. It's trivial example. That's why it happens.
because we are getting the same thing, that's why I went
Correct.
it. Though I
Okay.
can write here max and
Okay.
same thing afterwards, and we'll get the same thing. So that
Okay.
is why you can go either left or either down.
Okay.
That is the main thing here. Now, talking about S02, either we can S02 is we'll go basically down. Suppose we go choose the action down here. We can go left also, but suppose we choose the action down here. The optimal action, suppose, is the, like we'll get the optimal action by performing max only. But
Yeah.
suppose it's down here, then what will be the S02 here? Basically, again 0 plus 1 into 1, that is 1 here. And
Yeah.
if I choose the action this one, okay, we don't have S01 right now. Okay, let's proceed. S10.
So here it is 0, right? The next
Yes,
one is 0. Its max is what? From S02 going to S01. This is the max of this and 0, right?
yes.
0
No,
plus 1 into 0.
0 plus 1 into 0. We
Hmm.
can't say 1 into 0. because we are saying that we haven't calculated it. Does okay? Yes, yes,
Yeah,
yes.
initialize, no, initialize, no.
Initialize
Initialize to 0. Yeah,
Initialize to
initialize to, yeah.
because it's initialized to 0, so we will take, you are right, we'll take the max of 1 and 0, and then we are getting 1, so that is why we'll go down rather than going to left.
Yes.
Now coming to S10, S10, now what are the possible paths we can go?
Right or down or up also.
Right or down or up? What about up?
Up is 0.
Up is 0. What about right?
All are 1 1. Right and down is 1 1.
So basically I'll say that I'll get the 1 here. Now the updated is basically value function is this 1 0. I think something is wrong. S10 is also 1. S02 is 1. S21 is it correct?
Yeah. Till now it is correct. Okay. Yeah.
Now the next iteration, suppose S01. Now what are the possible paths we can go from S01?
Left, down, right.
Left, down, right. Left, what is the left? What is the value
0.
function? 0.
0.
Right,
1 1. Right 1, down 1.
so I can say that it will be equal to 1.
Yeah.
Now S10,
Same thing. Yeah.
same thing, 0 up,
Hmm.
right 1, down 1.
Hmm.
So can I
Correct.
say it is also 1?
Yeah.
So S00, I
Is
can go
also
left, right or 1, and both are 1, and max is equal to 1. So
Hmm.
basically with this I am getting though it was just a simple like how I am basically updating my value function. Nothing else. The main I can say the last example was much complex than this one, or we'll go with the more complex a more more example which I'll compare with the policy
No, it
iteration
helps.
as
It helps. I'm nothing. it helps. It helps. Yeah. Yeah. Interesting.
actually I'll solve
Yeah.
value iteration and policy iteration example after completing the policy iteration part.
Yes.
Any doubts till now? Should I proceed?
Yeah. Gopal, yeah. Bad, yeah, sir. Yeah, sir. Please proceed,
Madam, I have
Gopal,
a
sir.
question.
Yes,
Right
yes.
now in this value iteration, you are taking the max, right? Max of, but in some equation I saw expected thing of all the three. For example, you have three choices to go from one state to the up or left or down. Taking expected return of the three versus right now you are taking max.
Okay, I'll tell you. Now, what I'm saying is, suppose I have three actions, as you told me, A1, A2, A3. I'll calculate the expected return, I'll calculate the expected return of all of them, and then I'll check like which one is the maximum one.
Yes, that is okay. But if you are starting, let us say from state yes, you have A1, A2, and A3. So the value of the state, is it an expected return of A1, A2, A3 or max of A1 or A2 or A3?
Can someone answer the question?
Obviously, it is max. As per it, I mean, step number what, 2 or 3? Step number 3. You can show the step number 3. Yeah. Step number
Now,
3.
what this? It is
Step
max.
number 2. Step number 2 max. Yeah.
It is max.
Yeah. Max.
Actually, I have to calculate. We have to calculate the expected return. You are correct in that. We have to calculate the expected return. Now, I have to check that which action is giving me the maximum return, basically maximum expected return. Which value, which action is giving me? Argmax means which action is giving me the maximum of expected return here.
Okay, that is
step
yeah.
step number two. Step number two, ma'am. Step number two.
Yes, yes. So that to arrive at the policy, we use that optimum max to arrive at the argmax. Argmax of A will give you the policy.
Not argmax. Only max. Only max.
Ah, yes, yes.
Max will give me the value.
Max
If
value.
I want
Max
to,
value.
what is the difference between argmax and max here?
Yeah, argmax means it will give you the value of the type of the arm, which arm is
Which
giving
action-
the max. Yeah.
Yes, yes. You are correct here. So basically, policy is basically which action is giving me the maximum here. And the second step was which is the maximum value. How this is the updating equation. And then that is like I want to check that which action gave me the maximum this expected return.
Madam, one general confusion I have is, see, uh, uh, may I assume the objective of all reinforcement learning algorithms or agents is to come out with optimal policy, one optimal policy, okay? That optimal policy is a deterministic policy, correct? Or probabilistic?
It can be probabilistic as well.
Okay, okay. So that is the goal. Any algorithm you take, that is the goal. But let us take right now we're discussing value iteration, right? We discussed value iteration. Okay. So in the value iteration problem, but we also start with a policy, right? Going left or going right or going that is also a policy. So input also is a policy, and the outcome is expected also is a policy after iteration, correct?
Input is like, suppose I'm taking the actions. If I'm in a particular state, I'm checking like, okay, this action will be the best one, this action will be the best one. After that, got that, okay, if I'm in this particular state, this action is the best one. That is the policy. If I'm in a particular state, which action is the best one? I'm starting with the multiple actions here. Like I'm in a particular state, I'm starting with either I'll go left, either I'll go right, either I'll go down, either I'll go up. Then I conclude that, okay, if I'm in a particular state, this action is an optimal policy. This action is the best policy here.
Yes, yes, I got it. I got it. But see, there is another kind of problem called MDP problems. In MDP, we also give model that probability of moving to another state given S comma A. So I always, yeah, maybe you can throw some light. In what context we use MDP, in what context we don't use MDP. Yeah.
Okay. Can someone explain this answer, MDP and what?
So this is MDP only. But whenever we take an action, we with probability 1 we go to next state. Right here, I mean, action doesn't lead to multiple states based upon probability. Right? This is MDP only. But the whenever we take action, let's say go to left, it will go to left with probability 1.
Oh,
That is
okay. I got
yeah.
insight. Yes,
Yeah,
great.
yes.
Like
Thank
you were asking me in the last lecture only, like, okay, is this MDP or MDP? How we'll solve the MDP? Value iteration is a technique to solve the MDP problems. Like value iteration and policy iteration. Like we'll proceed with the policy iteration as well. These are the techniques to perform to solve the MDP problem. That is what we are doing here. Now here we are saying that it is deterministic. When we'll go to left, we'll go like we are not having the probability here, like either this probability or that is why that is missing. Like this is deterministic, that there is no probability involved. I haven't given the probability in this.
There is probability. This summation has only one term. Probability of S dash given S comma A is 1 only.
One only,
And
yes.
other probability. So there are implicitly there are. Yeah.
Yes, we can say in that sense that
Yes.
if we'll say one, then implicitly there is probability.
Yes,
And this is MDP only which we are solving. This is a technique. A value iteration is a technique to solve the MDP problem. Now, any doubt? Is it clear now?
Yeah.
Let's proceed. I'll come to more value iteration example after solving the policy, like after explaining the policy iteration as well.
But so you showed only one iteration, right?
Yes, yes, yes. We'll solve the more of the more iteration example after this one,
Okay. Okay.
because it was just a simple one. So that's why, just to give a overview.
Okay.
I have a question on the value iteration.
Yes.
So once we find the um, convergence on the value function, and we now find the appropriate policy using the argmax, and we get the pi. And now, if we were to calculate the value function using this pi, will it be same to the converged value function, or will it be close to that?
Like here we are saying that we are going epsilon close to that, as we'll see in this value iteration algo also, that vn plus 1 minus vn is epsilon close. We are saying that
Yeah,
it's epsilon optimal, so it's close
yeah.
to that.
So okay, so let's take that we stopped at Vn, and now we are calculating pi based on Vn, and in the step 4. And if we calculate v, if we again try to calculate v based on the calculated pi, will it be equal to Vn, or will it be close to Vn?
Okay, you are saying that if it is converged, if we are going, this condition is satisfied after this thing.
Yes.
You are saying after this.
Yes.
After this, it will be, we are sure that it's epsilon close to that. Because we have taken this condition. We are not saying that it is equal to, but we are sure that it's epsilon optimal.
No. That answer. That's not my question. My question is, in step 4, we are calculating a pi based on Vn, right? Yeah, Vn plus. We are calculating pi based on Vn plus 1. And now, if we were to calculate V of this pi, will it be equal to Vn plus 1, or will it be close to Vn plus 1? Because Sir had mentioned that the V here is not a value function, it's just a state of functions. And so if we were to back calculate like V of pi based on the after step 4, let's say we have some step 5 where we are saying we are calculating V of pi, will it be equal to Vn, or will it be close to Vn? Because Vn need not be a value function. It can just be a random function, right?
Yes, yes. Okay, you are saying that after we got this value function, then we are applying the pi, and the policy we are doing that, and then whether it will be close to, or whether it will be equal.
Madam, I think as I understand it, what he's saying is, let us say we arrived at optimal policy after iteration, and if you input that policy again and start over from the beginning, actually should reach the same, close to it only. It's like already converged. We once again repeat it, the whole value iteration with that converged policy as the input. The output again should be close to it only, no?
No. That was not my question. My question was value function with respect to that pi that we have. After step 4, we have a pi. Now, what would be the v pi of it? Will it be equal to Vn, or will it be close to Vn?
What do you mean by v pi of it? Can you elaborate this v pi of it?
Okay, just
No, I would like to add over here. Yeah. So V pi, see, after iteration, we are reaching towards fixed point. And the moment we derive a policy, and if we use that policy to compute V pi, we will be reaching to fixed point. So it will be very, very close, epsilon close to V star. So that is the case. Karthik.
so v pi is basically the equation that we have, right? Like
Correct.
sigma of all actions given
Yeah.
pi. So we know the pi. The pi is from result of step 4.
Yeah.
Yes,
And
yes.
we are doing that. We are calculating
So,
that v pi
yeah.
using that equation,
Correct.
right? And
Yes.
now, will that v pi of s be equal
Yeah.
to Vn, or will it be close to Vn?
It will be close to V star, epsilon close to V star.
No. It
Yeah.
not close to. I'm not asking about V star. I know it is close to V
And
star.
Vn also is very close to V star. Vn plus 1 are close to V star. So
I
these
know Vn is
coordinates
close
are,
to V star. V pi is
yeah.
close to V star. Will V pi equals Vn, or V pi will be close to Vn? Are the
Close
three
to.
three different value functions is my question.
It will be
Okay.
close to Vn. Yeah.
You are
Okay,
saying
okay,
V pi, we are saying V star, and then we are
Yeah.
saying
V
Vn.
pi and yeah.
Yeah.
V pi and V star, we know that they're epsilon optimal close to each other.
Yeah.
That's
Yeah.
correct. Now
Yes.
coming to V pi and Vn,
Yeah.
you're asking about this thing.
Yeah. Are they both the same or will they be different?
They'll be like same epsilon optimal close to each other.
So look at V pi minus Vn plus 1. This difference, the Euclidean norm, on the max norm of V pi minus Vn plus 1 is epsilon by
Okay.
2. Is epsilon by 2. That's
So,
what proved, no?
yeah, that is because V is not a value function, it is just a random function, right?
V?
No, sir, I feel that at the time of convergence, that Vn becomes V star. That's what I am thinking.
When it's
No, Vn is
epsilon close to V star.
epsilon close to V
Yeah,
star.
epsilon plus V star, whatever. Okay.
Yeah.
Right.
So I mean in the proof, no, in the proof of part C, V pi minus Vn plus 1, this norm
Yeah, it's less than
is
epsilon
by 2. Epsilon by 2.
Yeah. Yeah. Yeah.
Yeah. So it is epsilon by 2 close to V pi. Vn plus 1.
Okay.
Yeah.
Yeah.
It's like Vn plus 1 and V star are epsilon by 2 close to each other.
Yeah.
And
Vn plus 1 V
also
pi.
Vn plus 1 and V pi are also epsilon close to each other.
Yeah.
And that is the proof of
And that's
like
what
when
we'll
he's
do now.
trying to prove. Yeah.
Yeah. Yeah.
The reason is that Vn plus 1 is not a value function, it's just some random function, right?
Yes, yes.
It may be it's
Yeah,
a iteratively obtained function, not random.
Yeah.
Iteratively
But-
obtained function. Yeah.
Yeah.
I
Yeah.
can say
I mean,
that
I get it.
V
Yeah.
not the space of like space that corresponds to the value function. It is the space of function. We are taking the small
Yeah.
baby.
So, and that is the reason for this epsilon closeness. Okay.
Yes, yes.
Okay. Thank you.
So basically, Vn converges the same thing which we discussed now. V pi is basically epsilon optimal. Now coming to Vn plus 1 minus V star. Vn plus 1 is epsilon by 2 optimal. Let's go with the C part. So what do we mean by V pi is like epsilon optimal? Can I say that V pi minus V star is basically epsilon is less than epsilon? Is it correct to say that?
Yes.
Now we can apply the triangular inequality property here. Before that, we can let us add and subtract with Vn plus 1. Is it fine? So what is this? How we come how we came to this? Yes.
The triangular inequality.
Triangular inequality. I think I need not explain. If someone is having doubt how we came, you can interrupt me. I'll explain it. So now, suppose applying. Okay. Now talking about come back to that. Just write it and then we'll discuss it. Can someone explain me this? What is this equation? Yes. Simple, just now can someone explain me? Am I audible?
Yes, yes, you're audible. Yes.
Can someone explain me?
Yes.
Can someone try?
Yeah. So if we take deterministic actions, we get this. The first term is expected immediate return, expected value of immediate return as
What
per
is
that
this?
action. This is action. This is pi action as per pi s, which is deterministic action, which gives us maximum value. Yeah. So upon taking this action, we'll get expected return. The first term is immediate expected return, and second term is discounted return, expected discounted return.
So basically, there's no difference. Just I have in place of A, I have written pi of s.
Yeah. Yes.
Because this is deterministic. Whenever I am in S, I'll go to A.
Correct.
That is the policy. That is why I have written instead of A, pi of S, because it is deterministic. Whenever I am in A, pi of S will tell me, whenever I'm in S, pi of S will tell me go in A. The same thing, deterministic thing. That is why pi of S is written. Now, can someone explain me this thing? How these are equal?
This policy pi is determined from this our step number 4, which is R max A, step number 4.
Yes.
And then because it is returning max, L and L5 are same. That's why
Yes.
operate here.
So basically, it is like pi is giving us the max operating, like our policy is the max one. So and that is the deterministic one. So it is same whether we'll apply L or we'll apply L pi on V of n.
Yeah.
So now let us proceed to here. V pi minus Vn plus 1. Why I can write V pi as L pi of V pi?
Fixed point.
It is a fixed point. Now, again, I'll apply the triangular inequality. Now, can someone tell me how I get from this second like this one to this? What is the difference? This is the difference and this is the difference. Why I'm writing L Vn plus 1?
L and L5 are same.
That we have done now only. We like as you explained.
Yeah.
And what about this?
As Vn plus 1, it's LVn.
This also we have done in the previous lecture only, that we can write Vn plus is equal to LVn. Okay.
The next equation.
Wrote it as gamma, took it common. Take it at left hand side. V pi minus Vn plus 1. 1 minus gamma. Gamma Vn plus 1 minus Vn. V pi minus Vn plus 1. Gamma over 1 minus gamma. Vn plus 1 minus Vn. Now the second part, what was it? Vn plus 1 minus V star. I'm just writing it like this only, like we have in the last example when we were doing last lecture, when we were doing the contraction thing, then like I have proved like how we came to the summation term. Just here infinity is there. Similarly, as the last, the first part, I'm writing it like this. Taking common. GP. Now we know that Vn plus 1 minus Vn is
Stopping
less than epsilon 1 minus stopping criteria 2 by gamma. When we'll plug in the value, so we are getting epsilon by 2. Similarly, for the upper equation as well, we'll get epsilon by 2 here. And then we can say that here Vn plus 1 minus V star is less than epsilon by 2. And as we have written that V pi minus V star is less than equal to V pi minus Vn plus 1 by the triangular inequality, less Vn plus 1 minus V star, and both are like epsilon by 2 plus epsilon by 2. So I can say it is epsilon optimal. Yeah.
Yes. Yes.
Everyone, should I proceed? Now coming to policy iteration. Can someone tell me the difference between value iteration as well as policy iteration?
Madam, in value iteration, we focus on computing value. In policy iteration, we take an input, we take a policy, and we focus on storing only the policy or the actions for each state rather than the actual value. So, in value iteration, our focus is to get values for every state.
Yes.
Okay. In policy iteration, our focus is to get the policy. To get the policy means what are the optimal actions in every state.
Yes. So let us see how we'll go along, and then we'll give come up with an example so that we can get a better understanding about this. So basically in policy iteration, we are starting with an arbitrary, any random policy pi naught. Then we are finding v pi naught. Then we are being greedy with that, with respect to that. Then we are finding pi 1, and then we are finding v pi 1. This is how it is going on. Some prefer policy, it depends on the problem as well. Whether to prefer with the policy iteration as well as to the value iteration. So basically select pi naught. There are two steps here: policy evaluation and policy improvement, basically PE and PI here. Here, one more thing is there, like suppose going up and right. Suppose I'm taking the grid example, and going up and right, basically both are optimal steps. In previous step, you have chosen going up as an optimal action. Now this step also you have both the option, then which one you can choose? You can choose both, or like right or up. Can someone tell me?
Up. Retain the policy. Yeah.
So basically, it's better that whichever policy, optimal policy you have chosen, whichever optimal action you have chosen in the previous step, it's better to choose that action only if you are getting the same options. Like previous step, suppose up was the optimal action. Now you are getting a choice between up and right, both are optimal action. So it's better to choose the one with the which you have chosen as the previous one. That is what I want to say here. Policy improvement. One more thing I forgot, that stop if pi n plus 1 is equal to pi n, or I can say declare that pi n is equal to pi star here. Otherwise, go to step 2. So here, okay, let's go with an example now. I'll again go with the value iteration example and then solve with the policy iteration. A simple toy example we'll take. Suppose S1, S2, S3, there is a taxi. S1 is suppose the airport. S2 is suppose the city center. And S3 is suppose the railway station. Simply take like the reward from S1 to S2 is 20. Reward from S2 to S1 is 25. Reward from S2 to S3 is 15. S3 to S2 is 10. S1 to S3 is 18. S1 to S1 is, wait a second, S1 to S3 is 18. S3 to S1 is 22. Reward from S1 to S1 is 10. S2 to S2 is 12. Initially, V of S1 is equal to V of S2. Like basically they are 0. Now let's compute it. And gamma here is 0.9. So V of S1, I can say max of S1 to S1. What is the reward here? 10 plus 0.9. Is it correct? I have taken from S1 to S1, comma, S1 to S2. What is the reward here? 20 plus gamma, that is 0.9. And V of S2 is 0 basically. S1 to S3. What is the reward here? 18 plus 0.9. Max of 10, 20, 18, that is 20. Any doubts?
No, it's okay. Yeah.
V of S2. Now can someone tell me? Let's solve together. Max of, it is
25
iteration.
let's say S2 to S1.
Iteration 1. Let's clear it. S2 to S1. So S2 to S1.
25
25
plus
plus,
0.9 into is it in place computation or what? It's,
no, it's not in place. Like we'll take.
then 0.
Hmm.
S2 to S2.
S2 to S2.
It's 12
12.
plus 0.9 into 0
Hmm.
plus S2 to S3 is 15
Hmm.
plus 0.9 into 0. It's
So
25.
max of
25.
coming to V of S3.
S3 to S1 22. 22 plus 0.9 into 0 plus S3 to S3 to S2 is 10.
Okay.
10 plus 0.9 into 0 plus S3 to S3 is 8 plus 0.9 into 0. It's 22.
Now coming to iteration 2.
VS1 is max of 10 plus 0.9 into 20.
Okay. Now how 20 like S1 to
VS1. VS1.
okay.
VS1 is 20.
S1 to S1 is 10. Basically 10 plus gamma into V of S1 is 20 basically. So that
Okay.
is why we are taking this.
20.
Now reward. Now this
20.
was S1 to S1.
Yeah.
S1 to S2 is 20 the
plus
reward.
plus
This
0.9 in 0.9 into 25.
V of S2 25. Now S1 to S3, what is the reward?
18 plus 0.9
9
into
into V of
22.
S2 22. Can someone calculate? 10.9 is 18. 1.8.
1.8 plus 10, 11.8.
It's 18 only. 18 into that is 28. 25.
28.
22 into 0.9 is 19.8. 19.8 that is 37.8. So 42.5.
Madam, here in every iteration, the values are changing, but the reward function is constant, right? It is the same.
Yes, yes, yes.
The reward function is always, we are taking the same reward function values. Is correct? Rewards won't change.
Yes.
Okay, okay.
Okay, now coming to can someone tell me what is S2 to S1 reward?
25. 25 plus 0.9 into 20. 12 plus 0.9 into
Is it 20?
25. Yeah, 20.
V of
S1 in the previous iteration, 20.
previous iteration 20. Yes, yes.
Plus 15 into 0.9 into 22.
S2 to S2, what is the reward?
12. 12. 12 plus 0.9 into 25.
Okay. S1 to S3.
15. 15 into 0.9 into 22. 43. Max of 43.
Max of 43.
34.5.
34.5.
15 plus 0.9. 34.8.
So basically 43. So V of S3. Max of
22 plus 0.9 into 20.
22 plus 0.9 into 20.
10 plus 0.9 into 25.
10 plus 0.9 into 25.
Plus 8 plus 0.9 into 22.
8 plus 0.9 into
22.
So basically, okay, this is how, this was just a small example how I have solved these iteration 1 and iteration 2 for this. Now let us solve for policy iteration. just to get the difference between them. So policy iteration has two parts: policy evaluation, then policy improvement. That is what we'll do. Now coming to policy evaluation first.
What is pi naught? What is pi naught? P, the initial policy, all a uniform policy.
Okay.
We require a uniform policy or whatever we decide. Yeah.
Okay. Yes, let's take as like policy, like any uniform policy. S1 will go to S1, and S2 will go to S2, and S3 will go to S3. Any arbitrary pi. This is what we have picked.
Okay.
Everyone got it? What is this pi? Can someone else tell me so that I can know? Only like 1 to 2 or 3 people are listening, or everyone is listening? Can someone else tell me what is this I am doing? S1 to S1, S2 to S2.
I'm not able to follow, madam. S1, is that what kind of policy is that? Remaining
Okay.
in the same state. Yeah.
Okay. What I'm saying is, let us say that in the policy iteration, what is it? Select any pi naught. Select pi naught means I'll select any random policy first of all. Like we have that policy, either I'll go from S1 to S1 only, either I'll go from S1 to S2, either I'll go from S1 to S3. We have three things here: S1 to S1, S1 to S2, or S1 to S3. Now what I am taking is, let us take arbitrary policy. So any random policy, let us suppose I took it as, if I'm in S1, I'll go to S1. If I'm in S2, I'll go to S2. And if I'm in S3, I'll go to S3. Is it fine?
Say with probability 1. Other probabilities are 0. Yeah.
Yes.
Yeah. So that is the confusion. S1 to
Oh.
going S1 to S2 is 0.
Here
Going
actually
from
we are
S1 to
taking the probability 1, basically.
So, madam, so we can start with any policy, right? Any policy.
Yes, you are correct.
Any random policy.
That is.
I can choose equal probability also. S1 going to S2, S3 into one third. That also is possible. From S2 to S1 and S2 to S2 and S2 to S3, one third. That is also is a random policy, correct?
Yes.
So, for example, here you have chosen a fixed policy of S1 going to S1. So, but I said the policy could be any random from S1. You can go to S2, or you can go to S3. You can go to yeah. So similarly, from S2, we can go to S2. We can go to S1. We can go to S3. So it's.
I can write like this. This is what you are explaining.
No.
That's like
no. The starting state is S1, but from S1 I can take I can go to S2, S1 to S2, S1 to S1, S1 to S3, S2 to S2, S1 to S1, S1 to S3, like that for all.
What can you again repeat? S1 to
S1 to S1, S1 to S2, S1 to S3. It is equal, one third.
Can someone explain me?
Yes, we can take any policy. We can take any policy, any initial policy. But I mean, this makes calculation simple. S1 to S1, others are 0. So this makes calculation very simple. It's a very simple policy that she has selected.
That this is a deterministic policy. What you have?
No, this is not deterministic. This is simple policy. Very simple policy, not deterministic. There is a probability, a kind of deterministic. Yes.
Yeah.
We can say deterministic because we are not saying that we are saying with one probability. That is why we are saying it as data. So we are taking any arbitrary policy that S1 will always end up in S1. Like you said, 1/3 of time I'm going in S1, 1/3 of time I'm going in S2, 1/3 of time I'm going in S3. That is also fine. So here I'm taking a very simple like arbitrary policy that I'll end up if I'm in a state S1, I'll end up in S1. If I'm in state S2, I'll go in S2, and if I'm in state S3, I'll go in S3. So this is the first step. Is it clear?
Yes.
Second step is policy evaluation. What is the reward from S1 to S1?
S1 to S1 is 10.
10 plus what?
Gamma is 0.9.
0.9. We value of S1, we are taking initially 0 here, and then we are getting 1 here. What is the reward from S2 to S1? S2 to S2, sorry, because we are taking S2 to S2 here.
S2 to S2 is 12.
S2 to S2 is 12 plus 0.9 into 0, that is basically 12 only. What is the reward from S3 to S3?
8.
This was the first step, that is policy evaluation. Now we are going with the policy improvement. In last value iteration, you asked me about in place, or I can say asynchronous, synchronous. Can you explain to all of them so that we can proceed with that? What were you saying about in place basically?
Yes.
Okay, let
So
me
the latest the values which are calculated in the same iteration, use in the same iteration.
Yes. Can I say it as asynchronous?
Yes, asynchronous. Yeah.
Okay, I'll first do it and then I'll explain again. First of all, we have done with the policy evaluation. Now I'm going to do the policy improvement. That is R max of A. Basically, which one? N plus 0.9. Value of S1 is 10 only. Now going to what is value of what is S1 to S2 reward?
S1 to S2 is 20.
Okay. 20 plus 0.9. And what is the value of S2? 12. What is S1 to S3 reward?
S1 to S2 is 18.
18. And what is V of S3? 8.
Yeah, 8, yeah.
Now 10 plus 0.9 into 10, that is 19. 20 plus 0.9 into 12. 108, 108, 10.8, that is 30.8. 18 plus 0.9, that is 7.2. 18 plus 7.2, that is 25.2 approximately. So I can say that 30.8 is the max one, and R max we are saying, so S2 is the maximum one.
Yes. A is go S1 to S2.
S1 to S2 is the max one.
Is
I can
higher
say.
than S1.
Now we'll again go to asynchronous one so that we can get
No, madam, here just one confusion. While in the policy improvement, why are you calculating once again? Already the values are calculated, right? Evaluated in the previous step. we can find out from S1 which is the better option by looking at the values VS1, VS2, VS3. For example, if we S1 we are starting. Some S1 we can go to S2 and S3. Find out if you go to S2 is better or S3 is better. So S2 looks like better. So S1, S2 is the optimum action. So why are you calculating so many things?
Can someone answer the question?
So with the policy, given policy, we have calculated value functions. We have calculated value functions, and then based on this value functions, we have to select a policy.
Yes, that's
Update
what
the
we are
policy.
doing.
Yeah.
But selecting the policy, basically look at the current screen. So we know values of VS1, VS2, and VS3. Let us say that we want to calculate the policy of state 1, S1. From S1, S2, S3, we can move. So the movement to the always to the highest of VS2 and VS3.
There is reward also, no? Reward plus moving to highest. Discounted, highest, right? There's reward. R max, there is reward plus discounted next value function. There is reward.
Okay.
R max a reward plus this. Yeah.
Okay.
First, we are taking any arbitrary policy. Then we are calculating VS1, VS2, VS3. As he also told that we are having a reward here attached to that. So then we are doing the policy improvement. This was just the value function with the arbitrary policy which we have chosen. Here we are improving that policy. Policy improvement step is there. This is how the policy iteration works. First, we'll evaluate with any arbitrary policy. Then we'll improve that. We'll choose that which is the best action there.
Okay, ma'am.
Okay, now okay, where were we? Pi of S2.
This the equation, no? The equation which was written above, no? Just go on. Yeah. So this S1 and then H of VRP.
R max of S2. Now, can I say that it is S2? That is basically S2 to S1. The reward is
S2 to
S1 25, no?
S2 to S1 25, yeah.
Plus 0.9 into
V of S1.
Okay. Then S2 to S2, what is the reward?
S2 to S2 is 12.
Plus 0.9. And what is V of S2? 12.
12 only. Yeah.
S2 to S3?
S2 to
15.
S3.
15,
15, yeah. 0.9 into 8.
I can say by saying this is the largest one, 25 plus 9, that is 34. So S1, S2 to S1. Is it correct?
Yeah.
So now coming to pi of S3 here. S3 to S1, what is the reward? 22. Plus 0.9. What is V of S1?
10.
10. Now S1 to S3 to S2.
10.
Plus 0.9 into V of S2.
12.
12. S3 to S3.
S3 to
8.
S3 is 8.
V of S3, 8.
8, yeah. S3 to S1 probably.
I think,
S3
yes,
to S1, yeah.
22 plus 0.9 into 10,
Yes.
that is 31 basically.
Yeah.
This was iteration 1 here. Like we did 2 steps, policy evaluation, policy improvement. Let's
Yeah.
go with iteration 2. We'll like solve 2 iterations only. Okay, now the main thing is what we are saying here is that
V of
from
S1.
S1 where we'll go
S2.
S2.
S2. Yeah.
Why we'll go to S2? We got
So
it
this,
from the policy improvement
yes,
that when
yes.
we are in S1, the like the optimal policy or the policy, like when we are in S1, we have to choose, we have to go to S2. That is what we learned from here. Earlier, we were following any arbitrary policy. We started from arbitrary. We are learning here from the policy improvement here. Now, I can say, is it clear, everyone? Like
Yes.
why I'm doing this V of S1 to S2? Or are there any doubts?
Madam, the difference between value iteration and policy, in policy iteration, we are doing extra step of policy improvement, right? In the value iteration, the same value function, we are, whatever we get in first iteration, we are going second and third iterations.
Correct.
Maybe you can explain the difference later on. Yeah, it seems to be that we are doing more step, one extra step in policy improvement more than a value steps in iteration.
In 2 steps like policy evaluation and then policy improvement. Yes, you are correct in that thing.
Okay, ma'am.
And basically there we are okay, I'll tell you the whole differences. I'll show in tabular form and post in Slack basically so that you can get a better understanding. The policy we'll obtain later. Here we are updating that policy actually in every step. As you can see here, earlier I said that we'll go from S1 to S1. Now what we are saying that we'll go from S1 to S2. That is the optimal step that we learned with the policy improvement in the last iteration. You got it? How we got this one?
Yes, madam. That is what we discovered in the previous iteration, the policy. Yeah. Right.
Now what is the reward of S1 to S2?
20
Plus 0.9
into 12.
into 12. 30.89.
Yeah. And now this is the updated value. Yeah.
Now,
VS2. Yeah. S2 to S1 is the policy.
now this is S2 to S1 because as we learned that when we are in S2, we'll go to S1. That is what we learned in the last policy improvement. Now, what is the reward?
25 plus 0.9 into now latest updated value 30.8. Yeah.
Now, everyone is clear, like what is the 30.8? Suppose I take it as or
The
20.
previous value was 10. S1 was 10. Yeah.
Everyone is clear? What is this? What I'm trying to do here? Yes.
Yes, madam. We're just taking the previous value of S2. Just previous.
Last iteration value, we are taking this one only. This is basically called as asynchronous update. Like I have this VS1 and I'm taking here, but here I'm not having the value of VS2, so I'm taking the last iteration value. When I'm following this thing, like I'm always taking the last iteration values of VS1 or VS2, that is called as synchronous update. I did this just because one of you mentioned about this asynchronous update, so I thought, okay, let's start, go with this. I think it's clear. So 25 plus 0.9 into 30.8, it's how much is it?
To it, yeah.
30.8 into 0.9 plus 25, 52.72. V of S3. Now where we have to go?
S3 to S1.
S3 to S1. That is what we discovered. Plus gamma V of S1. As we are following
0.9
asynchronous update, again 30.8 I can say.
Yeah, 30.8. $49.72.
Now going with the policy improvement. So S1 to S1 10 plus 0.9. Value of S1 30.8. S1 to S2 20
Yeah.
plus 0.9 52.72. Value of S2. S1 to S3
18.
18 plus 0.9 49.72. I think 21 is the highest one, if I'm
Yeah,
not
20.9. Yeah, yes.
this is
Yeah,
52.72.
going from S1 to S2 only. Yeah.
So 95.16, and we'll go from S1 to S2 basically. So pi of S2 so S2 to S1
25.
25 plus 0.9. Value of S2 52 point, oh sorry, value of S1 30.8. Is it correct?
Yeah.
And S2 to S2
12.
12 plus 0.9 52.72. 52.72. And now S2 to S3
15.
15.
15 plus 0.9 into 49.72.
Which one is the highest?
I think the first one. Yeah.
First or
First or third, yeah.
okay, let's calculate.
Yeah.
30.8 into 0.9 plus 25. 52.72.
78 it is.
78. Okay.
Yeah. 59.502.
59.502.
02 plus 0.9. It's 59.748. The last one is. So third one is highest.
So S2 to S3.
S2
Can I
to
say that?
S3. Yes.
Now coming to pi of S3.
S22 plus
S2 to
0.9.
S1, that is 22 plus 0.9. What is the value function of S3? That is 49.
30.
Oh, sorry.
30.8.
30.8.
Yeah.
S3 to S2, what is the reward function? Reward
10, 10,
10
10 plus
plus
0.9,
0.9 into value of S2, that is
52.78,
52.72.
78.
78. Okay. Now, S3 to S3, basically the reward is 8 plus 0.9 into 49.72. So, which one is the highest?
Let's calculate.
First one. Okay.
49.72 is first one. First one is
49.72.
10 plus 0.9, 52 times 57.502.
2.
8 plus 0.9, 40,
52.74.
Yeah.
So S2, S3 to S2. So this is how the policy iteration and value iteration we have solved for the same example. Is it clear? Like what was the difference? Was it helpful?
Yes.
No, madam, the difference, can you explain? See, what I understand here is we improved the policy and taking the improved policy for the next iteration. In value iteration, the same initial random policy only we are iterating repeatedly.
Am I taking any arbitrary policy in value iteration?
Yes, you are taking some initial arbitrary policy, right?
Are you sure? In value iteration.
Yeah. So S1 to S1, S1 to S2, S1 to S3.
That is, I'm considering all the actions. I'm not saying it. If I talk about policy iteration, I'm saying that let us take an arbitrary policy that S1 to S1, S2 to S2, S3, as you also told me, that let us take 0.3 S1 4 plus 0.3 S2 and 0.3 S3. But here in the value iteration, I'm saying that we are going to, we are not taking any arbitrary policy here.
Oh, okay. But you are computing.
Yes.
You are computing values for all the actions and taking maximum out of that.
Okay, I'll give you more examples in the Slack. Solve it so that you will get the better understanding, and we'll also discuss the differences of value iteration and policy iteration in Slack.
Yeah. Can you clarify the asynchronous part once more?
So here we were saying that either like if I'll talk about V of S2, that is basically the reward plus gamma of V of S1. Now I'm taking V of S1 from this iteration only. I'm not referring V of S to the last one, to the last iteration, that is 10. The synchronous update is basically we have to refer to the last one. Actually, if we'll think intuitively, it's like we have to refer to the last iteration. But what I am saying here, I got the value of VS1. Let's take that update. Take that value only. That is basically a synchronous update.
Okay, got it.
Yes, any doubts? I'll suggest you once again go through this example to get the clear understanding. I'll upload the video after this lecture and discuss more examples, discuss more examples with each other also in the Slack group only, and solve this the code of value iteration and policy iteration also. If you want, I'll give you coding examples. I'll write in the Slack and I'll ask you to solve it. Should I proceed? Any doubts? Yes. Am I audible?
Yes, very much.
Yeah.
Okay. Should I proceed now? Any doubts?
Yeah, we can proceed.
I thought we'll cover Monte Carlo methods as well, but okay. It took time. Can someone explain me what is first of all dynamic programming? And are we doing dynamic programming in VI like value iteration and policy iteration? What is dynamic programming first of all? And the second question is, are we doing or not? I want the answers from everyone whosoever is present in the class.
Yes, madam. In fact, what we have done in value iteration and policy is nothing but dynamic programming only.
Yes.
Right. Dynamic programming means recursive updates from top down. In fact, that's what we have been doing. I don't know. I thought, yeah, that is dynamic programming. Yeah.
Someone else wants to answer. Yes, you are correct. Someone else wants to answer. Come on. What is DP, dynamic programming? Yes. I'll write it and then. Just what I have written, can someone speak and explain? Just what I have written. Is it correct, first of all? First question is it correct what I have written?
Yes, it's correct.
So can you explain this?
Yeah, it's one step. I mean, kind of iterative process. It's a one-step solution. I mean, yeah. From the previous step, I mean, go to next step.
So basically compute the solution for n sub problem and use it to solve it for n
For
plus
the
1.
next, correct.
So
Yeah.
as he told that we are doing dynamic programming in value iteration and policy iteration, is he correct by saying
Yeah.
this?
Yes, it is
Yeah,
correct.
and madam, and also we already proved that it converges, correct?
Yes,
Always.
yes, yes, yes.
So, may I say that dynamic programming always should converge, correct?
Can someone explain or tell your opinion about this? Is it correct or not?
We cannot say it. It really depends in case of dynamic programming. But for if it is a contraction operator, it will converge.
Yes, but any programming should terminate at some point. It
It really
cannot.
depends upon nature of the operations, right? If nature
Okay.
of the operations are not converging, it may not converge.
So
Here the
that means
nature,
the program will go infinite in that case, right? If it doesn't.
yeah, yes, it may.
One, give me the example. Okay, let's take as an homework example. Is there any problem in the dynamic programming which will not converge? All the DP problems converge as he asked the question. It's a homework problem for this class, or I'll expect the answers in the Slack as well. Is it fine?
Yeah, yes.
Madam, another question. This, in fact, implicitly we are using Bellman optimality equations, right? Here in this.
Yes, yes.
Yeah, we are using Bellman value equation.
Yes.
Yeah. Okay.
So what? Okay.
No, actually, the objective of dynamic programming, if I understand correctly, recall my school days optimization technique, that goal is to converge only. It should converge to find the optimum value.
I'm not saying you are incorrect. I'm just saying write the answer in the Slack.
Okay.
Maybe you are correct, maybe you are incorrect. Let's see. I want your opinion, everyone's opinion. If you are not, like, if someone thinks that he's incorrect, please give an example why he's incorrect in the Slack. Let's discuss. Okay, what is it? What I have written? Can someone explain? Let me complete, then we'll discuss. We have discussed this thing many times, like what is the difference, what we are doing here. Can someone tell me what is the difference between both of these?
Madam, one thing in the notation, the pi of A given S, right? You have written pi of S comma A. What is the correct notation?
Okay, I'm sorry. You are correct here. Now, can someone tell me what is the difference?
So in the first one, we are starting with the state S,
Hmm.
and then we are following some, like, we are
Mhm.
considering all the possible actions and the possible resulting states.
Hmm. And what
And
about the
then
second one?
second one, we are fixing the first action is fixed. So we are just telling that at that state, we are taking this action A, it might not be optimal. And then from there on, we are following it need not even follow a policy. And from there on, we are just following the chain of policy and then trying to get the average value of Q.
Yes. So we have discussed it many times. So what is V and what is Q? Which one is the V and which one is Q here?
The top is V and bottom is Q.
Yes. Though I wrote it, but yes, you are correct.
Yeah.
I don't think so. Now someone should have doubts. Still, I can explain like why it is V, why it is Q. Anyone?
Yeah, okay. In the Q pi of S comma A, we are fixing the action and then evaluating the state.
We're fixing the first action, not
Fixing
all
the-
actions. Yeah.
Fixing the first action. That
Yes.
is the in V pi, we are taking all the actions.
Hmm.
Of the-
So you are correct that we are fixing the first action. We are in the state, we are fixing the first action that it should be this A. So whether it is optimal or not,
Need not be.
yes, you are correct. Need not be.
If it is A star, it is optimal, but otherwise need not.
It need not even follow a policy that we're using to generate the trajectory down below, right?
I didn't got you. Can you again repeat?
So that A need not be following the policy that we are using to generate the trajectories down below, like from the resultant states, the 3 states. From there on, we are following a trajectory and we are using a policy pi. And the first
Hmm.
action need not be even part of that policy, right?
Yes, the first action need not be the part of the policy. It need not be an optimal action, basically. It's just, we can say, a random action which can be optimal, which cannot be an optimal, and it's not following this trajectory. So that is what is here. And we are basically doing DP here. We are computing the solution n step, and we are doing it for n+1 step here. So I can say here that both value iteration method DP and policy iteration basically both are DP methods which converges to V star and pi star, both of them. Now coming to asynchronous DP. Now can someone explain me after this example that what is asynchronous DP? Yes. We discussed about asynchronous DP. Someone asked me also the doubt. Again, I explained. Now
Yeah.
yes.
Karthik, go ahead, Karthik.
So if I understand correctly, like in policy iteration, we are sorry. Yeah, you mentioned that like we need not use the previous steps value necessarily. We can continuously update and then use that. So it's the value function is kind of moving within the same step, like or we are not using the last one's value, right? So that's what you said. So if we need not use n+1, like we need not use nth step value function to update n+1, we can still use n+1 for some states which were already visited.
Yes, you are correct. That what we took is like we were solving Vn+1 and some like we got V2 and V1 before that only in that iteration only. So we solve like we didn't took with the last iteration, we took that V2 and V1 suppose for the V3 which we have to solve with that particular iteration only. That is suppose iteration 3, we have V1, V2, V3. When we are solving V1, we are taking the V2 and V3 values from the last iteration. When I'm solving V2, I need V1 and I need V3. I need V1 suppose. I'm taking it from this particular iteration only. We are not referring to the last iteration. That is what we did in policy iteration example.
Yeah.
So,
Madam, if you go by that, then it is not the definition of dynamic programming, right?
basically, it is asynchronous dynamic programming, I can say. It is not sequential in nature. You are correct. If we go with the traditional synchronous dynamic programming, it is like we are taking the previous iteration.
Yes.
But if we talk about asynchronous nature, we are saying that sometimes we are referring to the value functions which we are getting in the same like iteration as well. Or I can say that it is not necessarily sequential in nature.
Okay.
Am I correct?
Yeah.
Correct,
So,
but
Yes.
does both those methods, synchronous and asynchronous, converge to the same result?
They both converge, but sometimes asynchronous DP basically is tricky in nature because we are not referring to the previous state and it becomes confusing as we saw in the example as well, but both of them converge.
Okay. And just to clarify, we're not assuming any Markovian process here, right? Markovian nature of the system.
Yes. Now, can you explain everyone what do you mean by Markovian nature?
So we are like, if we reach a state S, we are in Markov process, we say that irrespective of the history, there is only one value associated with it. Whereas in non-Markovian, it depends on the trajectory or the history which it used to reach there.
Yes, you are correct. That basically Markov process says that you only that the current state only depend on the previous last state. It doesn't depend on the all the history basically. It only depend on the last state. That is what is Markovian process. Non-Markovian process means we are depending on whole history, past events, as well as the last state.
So here it is not Markovian, right?
It is not.
Yeah.
No, madam, I'm confused here. I assume here we are assuming Markovian.
Here is, wait a second. It is Markovian. Yes, yes. Why? Yes, it is Markovian. I'm also getting confused. Yes. Why you are asking that it's not Markovian? Can you explain? And why you are saying Markovian? Let's discuss.
No, sorry. I think no. I got confused with Monte Carlo. Monte Carlo is not Markovian. This one is Markovian, right?
Yes, yes, it's Markovian. We'll go to Monte Carlo and we'll discuss about it.
Okay, yeah.
Monte Carlo is also Markovian.
But with asynchronous, we can randomly pick any state and update, right? It need not even follow the trajectory, right? Like the extreme case where we can just randomly pick some state and then update, and then like it's basically exploring all the states. It need not even come from the trajectory, right? So sir had mentioned, I think this is what he tried to mention in one of the videos.
Yes.
Yes, madam. I think that's the same doubt I have. So either in value iteration and policy iteration, we can start from any state, right? Any state, and follow the policy, correct? You should do the same result.
Is he correct by saying that by solving value iteration, policy iteration, we can start with any state? Yes, we can. Yes.
Okay. And another, the last confusion is asynchronous and synchronous. Yes, you said both converge, but do they converge to the same function, same value? Same value.
Yes, it will converge to V star basically.
Okay, so that means same. So yeah, one can follow either of these two methods, right? So okay.
We'll discuss more about asynchronous and synchronous in detail when we'll go through the time dynamic programming, generalized policy iteration. Then we'll go with the synchronous.
Because there should be a mathematical proof, but the process seems to be different than a dynamic programming. But so there should be some mathematical proof that both converge to the same result.
Let's go in detail in the next.
Okay, ma'am.
Today, policy iteration, value iteration, is it clear?
Yeah.
I came up with the Monte Carlo example as well, but as we are not having time, I'll not start with that. So
yeah, it's like sorry, just a question on asynchronous DP. Even if we are doing some random states and updating it, we still assume that it is Markovian, right?
We'll assume that it's Markovian, because if we'll not like
okay.
Depend on history. Yes, it will depend on the last state only. That is what.
Okay, yeah.
Okay, any doubt? Okay, if you'll have any doubt, let's discuss in the Slack whatever the questions which were discussed in the class as well, and come up with the coding examples. I'll expect some coding of the same example. Let's take the same example and solve it okay, not the same. I think it will not converge. Okay, some value iteration and policy iteration coding example. I want to see I'm expecting from you guys that you will post in the Slack group. Any doubts?
No. Like the general policy iteration we'll cover in the next session, right?
Yes, generalized policy iteration, real-time dynamic programming, Monte
Okay.
Carlo will cover in the next lecture.
Okay.
So, yesterday class was there or?
So there were only like couple of us, and he had switched it to Google and chat instead of this Zoom due to technical issues. And since there were only two, he said he might do an extended session for tomorrow.
Okay. I think he'll discuss about Monte Carlo methods, though we'll discuss in the next lecture as well.
Yeah. Okay.
Okay. Thank you, class.
Thank you. Thank you.
Thank you. Thank you.
Okay, thank you.